Resonance. So resonance occurs when we've got the driving frequency is equal to the natural frequency. So for instance, if we had a spring with a mass on it, that mass would want the spring would want to oscillate at a particular frequency. It's with a spring, it's to do with the spring constant of the spring. Okay, so that's going to want to vibrate up and down at a certain frequency. Now, if you imagine that we attach that to a plate that's attached to a vibration generator. So this vibration generator is going to go up and down and up and down and up and down. Now, to start with, it's not going to affect the amplitude at which this oscillates too much. But when it gets to the frequency at which this wants to oscillate, its natural frequency, this is going to oscillate with much bigger amplitude. So the graph you need to know for resonance is that this is the frequency of our vibration generator or whatever is causing the driving frequency. Now what happens is you always get the amplitude there. That will just be the amplitude of the driver. So if this is pushing up and down by 1 centimetre, it's going to push this up and down by 1 centimetre, okay? Nothing more until it gets to resonant frequency. What will then happen is you get a graph. The shape of the graph is sort of like that. So as the frequency increases, we've got an increased amplitude. Now, when you're drawing this graph, if you have to draw this graph tomorrow, make sure you put a label on it here. This label, that is how you can tell the natural frequency of what it is that you're oscillating. So it's a natural frequency of, in this case, of this mass on a spring. It's what this wants to oscillate at. When that natural frequency is matched by the frequency of that, you get a peak on your graph. Okay, so you need to know this graph. You need to know its amplitude against frequency, and you get a peak at the natural frequency. Now, quite a lot of times you don't want resonance. Sometimes you do want resonance. Useful applications of resonance, the easiest one to talk about is in a microwave. You match the frequency of the microwave with the natural frequency of a water molecule. The water molecule vibrates at a bigger amplitude and heats up your food. But a lot of the time you don't want resonance, okay? So bridges falling down, that sort of thing, that bridge, is it the Tahoma Narrows Bridge falling down? You don't want that to happen. So you're trying to damp a system. If we've got damping on a system, if this sort of sharp bit here, that shows that it's not very well damped, okay? It might be lightly damped, but not very well damped. A damped system, it would look more like that, okay? So we get this bit sort of spreads out. You can have different degrees of damping, and that's sort of what you're usually sort of aiming for when you're damping something for the resonance. So resonance sometimes is good, like the microwave. Sometimes it's bad, like the bridge falling down, because the wind frequency matched the natural frequency of the bridge, and the wobbly bridge in London, the Millennium Bridge, people walking across match the natural frequency. So we got big amplitude things. So what we do about that is we do damping, okay? Sometimes resonance can just be annoying or weird. So the trick where you smash a wine glass by singing, or make a wine glass vibrate by rubbing your fingers around the top of it to make a noise. Or there's that urban myth of brown noise, but don't Google that until after exams, please. Okay, anything else you want, let us know. I'll check this again probably about 6:30. Okay, bye-bye.